Hello everybody, it's Seokhyun again, and today I'm here to talk about simple harmonic oscillators and simple harmonic motion. Um, so this topic is not as hard as it seems. If you want to understand the real fundamentals of this, it's going to be a bit more difficult, but for the purposes of taking the exam and solving practice problems, harmonic motion isn't actually that difficult. Um, so let's get started. When we're talking about simple harmonic oscillators, most of the time, how we're going to look at it is a string attached to some mass with mass m. And we're going to start by pulling this string by distance x, and this thing is going to start oscillating. So the block is going to go in, and then it's going to get compressed by a distance of x, and it's going to get extended by a distance of x, and theoretically this would happen until basically forever because of Newton's first law, granted that there isn't any sort of resistive forces like friction or air resistance. This can go on forever. That's why it's called a simple harmonic oscillator, because it oscillates. um, so when we're trying to solve some sort of a problem using these oscillators, there's mainly two things that we need to know. The first thing is the period of such an oscillator. Now, when we think about a string, or a spring to be a spring, we know its spring coefficient, which is mostly denoted as k, but there's a lot of different things we can do with springs. For example, we can have two springs instead of one. We can attach two strings together in series and have a block attached and make this an oscillator. So we can't really just say k, and I'm gonna use k net in this case because we can basically determine the spring coefficient of everything that's attached to the block, not just this one spring. If there's more springs, the spring coefficient changes. So because of that, we're just going to use k net for that purposes. And the period of an oscillator, um, often denoted as t, is how long it takes for the oscillator to oscillate once. Um, so the unit of the period is in seconds, and this is often denoted as 2 pi square root of k over m. That's often denoted as the period. Or there's a lot of different things to this actually, because when we think of an oscillator's motion, right, it's going to go extend, decrease, and then extend back and stuff like that. We can actually graph this onto a circular graph, basically, with the particle moving at a constant angular velocity known as omega, and the position of the block here is just the x components of where the little particle that's moving in the circle is at. That's another way of thinking about harmonic motion, and the period of this entire thing would be 2 pi, which is the total angles in radians that this block has to go, over omega, which is the angular velocity. Um, Angular velocity, angular momentum, all that stuff. I look at Eamon's video or any other video on rotational motion. That will help you a lot on understanding what this is. But basically, that's the period. And in this case, omega is square root of m over k um, for a harmonic oscillator. And k here is just k net that I mentioned above. And yeah, that's basically what you need to know for the period of an oscillator. It may seem daunting. Just don't overthink a lot of the questions that you're gonna get. Like, it's if you're gonna have to answer, oh, what's the period of this harmonic motion? All you need to do is find the k net of the block and then figure out um, what the period is after that. And the second thing that we need to talk about is the energy of the oscillator. Now, I if you have been studying physics, you probably know that the energy of a spring, which is extended by distance x from its natural position, has the potential energy of 1 half kx squared. Um, so that's basically the energy of the oscillator. That's pretty useful for us. And we're going to break the oscillation down into different parts. And we're going to look at the energies that are present in each step. So first we're going to start at the position where we extend the block by x. We're going to pull it out by a distance of x. And the block isn't moving right now, so the kinetic energy here is 0. But the potential energy is 1 half kx squared, right? Because the spring is extended by a distance of x. Now, we're going to look at the time when the spring is back to its natural state, which means that it's extended by a distance of 0. There, we don't know what the energy is, but we know the potential energy of the spring, which is 0 because the distance that's extended by is 0. So we can figure out the kinetic energy here because of the conservation of energy. So kinetic energy final plus the potential energy final is the initial kinetic energy plus the initial potential energy. So we don't know that. That's 0. That is also 0. So 1 half kx squared is the kinetic energy final, which is 1 half times the mass times v final squared. So we can figure out that v final squared is square root of k vf. V final is square root of kx squared over m. So this is helpful when figuring out, oh, what's the velocity of the block at when the spring is at its natural state? Well, that's how you figure that out. And also, it's important to note that this is at time equals 1/4 of the period of the total oscillation, because an oscillation it's at distance x, it goes to the natural distance, it gets compressed by x, the spring, it goes back to its natural state, and then it goes back to distance x. So that's it. That's one period of the oscillation. So this position right here would be after 1/4 of the oscillation has passed. At 1/2 of the when 1/2 of the oscillation has passed, right, or the period, then this means that the distance is compressed by x. We don't know the kinetic energy here. We do know the potential energy because it's compressed by x times negative x squared is 1 half kx squared. So the kinetic energy here would be 0, right? Because of the conservation of energy, the potential energies are the same. The kinetic energies are also going to be the same. It's not going to change at all. At t equals 4 3/4 of the period, we're back to this position, so the energies are the same. And at t equals the period, we go back to the initial state where it is extended by x, and we have the same energies there. So this is basically all you're going to see on any exam or any sort of thing that you're going to take on harmonic oscillators. The only thing that you might see is the spring being dangled down from the top. In this case, the natural distance slightly shifts. So what the natural distance of a spring is when the spring or the system itself is at is at equilibrium. And you might say, what does equilibrium mean? Well, equilibrium stands for when the block and everything is just not moving when it's completely still. Um, so if you just put a block on a table, that system is in equilibrium. So similarly, the spring block system will be in equilibrium here when the spring and block aren't moving. When we pull the spring by a distance of x as we see here, the block is going to want to go back because that's what springs do. So this system is no longer in equilibrium. This system is oscillating. And that's why, and it's doing a specific type of oscillations called simple harmonic oscillations, and any other oscillations, I don't think that you're ever going to have to deal with them. Um, so just don't forget about the other oscillations. But going back to um, this situation here, so let's draw the free body diagram of that block with mass m. It's obviously going to feel the force of gravity, and it's going to feel the force of the spring pulling it towards the natural distance of, or towards the original distance of the spring, which would be k times x when this is extended by x, and that is going to be mg. So for the system to be in equilibrium, the net force acting on this block has to be 0. So that means the force of the spring will be equal to the force of gravity. So the distance x would have to be mg over k. So what this means is that if you just hang the spring or hang the block on the spring is going to have to naturally extend itself by a distance of x, and it's going to stay there, is basically the idea. So the new distance x, so this position here is the natural distance now. So don't just remember that this is the new natural distance. So the original length of the spring, if it's not draping down by a distance of x, this actually is no longer equilibrium as it was up here, where when it's not draping down or when the spring isn't extended, that was equilibrium up there. Down here, no longer is. That's the one little thing that shifts here. Everything else is the same thing. So here, we can do the same thing as we did above. Let's say this is time equals 0, so we're at equilibrium. The distance is extended by x. U, the gravitational potential energy, let's just say that is 0, plus the spring's potential energy is 1/2 kx squared, which is 1/2 m squared g squared over k. But let's just, which is that, yeah. And let's say that we're going to pull that spring by an additional x prime. So the total spring extended would be x plus x prime. That's how much it would be extended by. So the u would be 1/2 kx plus x prime squared plus mgx prime, right? Because it's draped down plus x prime relative to the 0. So that's how you would do the potential energy here instead of just the 1/2 kx squared as we did up here. And we can do the same thing as we did up here to get the energy at each time step, per se, of the oscillation. For me, this is basically all that I knew about harmonic oscillators when I took the exam. This was more than enough for me. Just remember the equilibrium, remember what springs do, and that's basically the gist of harmonic oscillators, using springs. There's another type of harmonic motion, which is a pendulum, a spring, or a string of length L, and a mass of m is attached to the end of the spring. The period in this case is 2 pi square root of I think it's L over G. Um, so that's the period instead of 2 pi square root K over M. So that's the little difference there. But yeah, that's basically the gist of harmonic oscillators. There are some more complex problems that could pop up. For example, what happens if you attach a rod with two strings and it's going to oscillate? These problems you probably won't see on the exam. There's a lot of different variations that you can do with these oscillators, which make them hard. But for the purposes of the AP exam, you don't really need to know any of that. So, thank you for watching this very short video.